Hey, welcome. We all learn that one simple rule for electricity, right? Watts equals volts times amps. But what if I told you that for the power that's humming through the walls of your home right now, that simple equation is, well, often wrong? Let's dive in and solve what I like to call the AC power puzzle.
Visit youtube.com/avidsystem and don't forget to subscribe.
So this is the core mystery we're tackling. We expect the power we use, the stuff measured in watts, to be a really straightforward calculation. But in the world of alternating current, or AC, which is what powers our daily lives, there's a fascinating twist. Turns out the total power that's supplied isn't always the same as the power that actually does the work. So here's the big question. If that simple formula, power equals volts times amps, works perfectly for things like batteries, direct current or DC, what on earth changes when we switch to the AC power coming out of our wall outlets? What's the missing piece of the puzzle here? And here it is, our first major clue. The solution isn't to throw out that old formula we learned. It's about expanding it. We have to stop thinking about power as just one single thing and start seeing it as a team of three distinct players, and each one has a very different job to do. So let's meet these three types of power. And to make this really clear, we're going to treat them like characters in a story. Each one has a name, a role, and a totally unique contribution to the whole system. First up, let's talk about the hero of our story, real power. We represent it with the letter P. This is the power that does all the actual useful work. It's the energy that toasts your bread, lights up your room, or makes a fan spin. It's measured in the good old watts that we're all familiar with. So a great way to think of real power is as the worker. It's the muscle of the team, right? It's the part that's physically moving the load and actually making things happen. All effort, all results. Okay, next up, we have a much more mysterious character, reactive power, or Q. People often call it wattless power, which is a cool term. This power is absolutely essential for any device with coils and magnets. Think about things like motors or transformers. They need it to build up and sustain the magnetic fields that make them run. But here's the catch. This energy doesn't perform any final work itself. So if real power is our worker, think of reactive power as the support system. It's kind of like the scaffolding on a construction site. It's not part of the final building, but you absolutely could not have built the building without it. It's necessary, but it's not directly productive. And that brings us to our third and final character, apparent power, or S. Now this is the total power the utility company has to generate and send down the power lines to your house. It includes both the worker power and the support system power. This is what you get when you actually multiply the total volts by the total amps in an AC circuit. So let's call apparent power the total effort, because from the power company's point of view, they have to supply enough energy to cover everything, both the useful work getting done and the support system needed to do it. Their entire infrastructure, from the giant generators all the way to the wires in your wall, has to be big enough to handle this total amount. Okay, so we've met our three characters. We have the worker, the support system, and the total effort. But how do they actually relate to each other mathematically? Well, that is where we get the power triangle. It is a beautifully simple visual way to put this all together. This little diagram illustrates the relationship perfectly. You start with real power, which forms the flat base of a right-angled triangle. Then you've got reactive power, which is the vertical side, going straight up. And the hypotenuse, the longest side that connects them both, is the apparent power, the total effort. Because these different powers are out of phase with each other in an AC circuit, they combine geometrically, not just by simple addition. This chart pretty much sums it all up. You can see our three power types, their symbols, and their units. But the absolute key here is in that last column, the formula. Because they form a right-angled triangle, they follow the Pythagorean theorem. And that is the mathematical key that unlocks our whole puzzle. Volts times amps gives you S, the apparent power, not always P, the real power in watts. All right, now that we have this triangle, we can get an incredibly useful piece of information from it. It's called the power factor. And the best way to think about it is as a simple efficiency score for any electrical circuit. It's like its report card. So what is power factor? It's simply the ratio of real power, that's the useful work, to the apparent power, the total effort being supplied. You just take P and divide it by S. The result is always a number between 0 and 1, where 1 represents absolute perfect efficiency.
Obviously, the goal is always to get a high power factor as close to 1 as you possibly can. That means your support system of reactive power is really small compared to the worker of real power. A low power factor? That's bad. It's inefficient. It means a ton of the total effort from the utility is just being used to support the system, not to actually get any work done.
This quote just nails it, doesn't it? Power factor isn't some abstract number. It is a direct measurement of effectiveness. It answers the one question that really matters. Of all the power being delivered to me, what percentage is actually being used productively? Now, at this point, you might be thinking, okay, this is some neat geometry, but why should I actually care? Well, this little triangle has a very direct connection to the real world of energy loss and, maybe more importantly, money. A low power factor has some pretty serious consequences. To get the same amount of useful work done, a system has to pull a much higher total current from the grid. And that larger current flowing through wires just generates more heat, which is nothing but wasted energy. In fact, because of this waste, utility companies often penalize large industrial customers who have low power factors by charging them extra on their bills. Let's make this really concrete. A power factor of 0.7 might not sound too bad, but what it actually means is that for every 100 units of power the utility company is sending you, only 70 of those units are doing useful work. The other 30 are just circulating around the system as reactive power, building magnetic fields, heating up wires, and costing money without contributing a single thing to the final task. And that really brings us to the main takeaway here. The power triangle, it's not just a clever bit of geometry for a textbook. It is a fundamental diagnostic tool. By understanding it, engineers can measure power factor and then implement solutions like adding capacitors to a circuit to dramatically improve efficiency, save energy, and, of course, reduce costs. So the next time you plug something in, especially a device with a motor, think about this hidden world of power. That simple little equation we all learned as kids has a much richer, more complex story behind it. And it kind of makes you wonder, right? In all the electrical systems around us, is the energy we use working as hard as it could be? Thanks for tuning in to this explainer.
Thanks for watching.